What's up, guys? And today we are going to discuss one of the most talked about and most asked question, that is distributed logging. And you've been using this for a very long time, since the starting of your career, I guess, because without logs, nothing works, and that is a minimum requirement of every system. Now the production goes down, users can't log in, and your team spends next 90 minutes grepping through the log files across 200 servers because nobody knows which one actually has the error. It turns out it was a misconfigured environment variable on a specific pod. One line in one log file and on one server that nobody thought to check. Every commercial airplane has a flight data recorder, not to prevent crashes, but to reconstruct exactly what happened afterwards. Which sensor fired, in what order, at what altitude. Your distributed logging system is that black box. Without it, when production goes wrong, you're guessing. With it, you know. The difference between 90 minutes of grepping and 5-second query that pinpoints the failing pod. So today we are designing a logging system that can ingest millions of log files per second and let you search them in 5 seconds. Let's go through the function requirement quickly. We need to collect logs for 1000 plus services. Then we need to store logs reliably. We need to be able to search in the logs. We should be able to filter and aggregate logs, group by service, count the errors, alert on patterns. If error rate is greater than 100 per minute, then do a page on call. Then we should be able to export the logs according to the compliance and do archival, do security audits. The difference from metrics is logs are text, unstructured, high cardinality. You can't aggregate them the same way. This distinction is worth making here. Logs and metrics are not the same thing. Shouldn't be the same system. Metrics tell you a number, error rate in 3%. Logs tell you the story. Failed to connect to DB at 10:32:15 on node prod east 1A. Connection timed out after 30 seconds. Retry 1 of 3. One number, one story, different tools. Don't try to use one for the other. So let's start with the math because it's humbling. We see that we need 1.3 petabytes per month raw. Then compression brings it down by 10x, but you're still talking about 130 terabytes of compressed storage every month. And that's before you even thought about search indexes on top of it. We go to the NFR. In throughput, we need 1 million log lines per second ingestion, then source latency should be less than 5 seconds for last 7 days. Retention for 30 to 90 days, we need to do it in hot. 1 year of cold archival, the availability should be 4 nines, logging must survive during the outages. Then the cost, we need to minimize the cost because we store a lot of logs. Here is the thing. The cost line isn't there by an accident. Logging at the scale can generally cost you more than the services it's monitoring. That is why we designed tiered storage. Not every log needs to live in an expensive search index for 90 days. Okay, after the non-functional requirement, here is the most important part, that is the high-level design. Think of a postal service. Each house, each service produces mail, which are logs. A local carrier, the log agent, collects from each house on a route and brings it to the sorting facility, the collector, which organizes stamps and routes. From there, some mails go to the local delivery for recent searches, some goes to the long-term storage for archives. A pattern scanner along the way flags anything suspicious. So these are the components. The first one is the log agent that runs as a sidecar on every service, tailing logs files or reading from std out. It batches every 5 seconds and send it to the collector. Lightweight, under 50 MB memory, this is running on every single service in your fleet, so it can't eat resources. Then we have log collector that parses and enriches, adds host name, region, version, then publishes to Kafka partition by a service name. Kafka is the buffer. If Elasticsearch is slow, logs queue here. If a processor crashes, logs replay from the committed offset. Kafka retains logs for 24 hours as a safety net. Then we have the log processor that consumes from Kafka in parallel, writes it to two places. Elasticsearch for hot data that lasts around 7 days, fully indexed, searchable in seconds. Then S3 for cold archival that lasts 90 days. It's in parakit file, cheaper, and we can query it with Athena. Then we have the alert manager that runs on the same stream and does pattern matching. If the error count exceeds 100 in 1 minute for a service, then page the on-call person. After discussing the high-level design, we can go a deep down on the API and the data model. The most important data model decision you will make in the system is whether you use structured or unstructured logging. Now, let me show you why it matters. The unstructured log is grep only. The structured log is searchable in every dimension by service, by error code, by duration, and by trace ID. We should always use JSON logging, always include a trace ID, and always include the service name. Here is the query API that we use for the log. These are the different filtering mechanism. We filter by the level, the service name, the from and to date, then the connection timeout, and the limit. And this is the format for the response. How we will get it, the pagination, and the next cursor is already included in this. This is the schema for the alert. We write the service name, the query, the window second, the threshold, and the notify elements. Whoa! Now we've got the 360-degree view. We should deep dive in some of the main components, and that's a must. These are the three components which we are going to discuss today. The first concept is log enrichment pipeline. A raw log line is just text. The enrichment pipeline transforms it into something queryable, and a lot of this enrichment doesn't come from the service itself. It comes from the agent's environment. Stage 1 is parsing. We extract the timestamp, log level, service name, message. Handle multiple formats, JSON, log FMT, plain text, because you'll have all three in a real fleet. Then stage 2 is enrichment. We add fields the service did include. Hostname, IP, region, service version, Kubernetes pod name. The service shouldn't need to know where it's running. The agent injects that context. Then stage 3 is the normalization. Standardize timestamp to UTC, normalize log levels. Warn becomes warning. We should strip the passwords and token. Every team I've worked with has learned the PII scrubbing lesson the hard way. Better to build it and start from day one. The result of this is every log line has the same structure regardless from which service it is emitted. So you can query across your entire fleet with the same query language. Coming on to concept 2 is the hot, warm, cold storage tiers. Think of it like your desk, your filing cabinet, and a warehouse. Your desk, the hot tier, has what you need right now. Immediately, accessible, expensive space. Your filing cabinet, it's a warm tier. Your last month's stuff takes 30 seconds to find, it's cheaper. Then the warehouse is the cold tier. It has the compliance archives from years ago. It's really needed and it's very cheap. Now the last 7 days goes to the Elasticsearch. It is fully indexed, sub-second search. 7 to 30 days goes to Elasticsearch warm nodes on slower hardware. It's still indexed though. Then the 30 to 90 days moves to the S3 packet. Queryable with Amazon Athena or Presto in minutes rather than seconds. 90 days and beyond goes to the Glacier archives. Compliance only, hours to retrieve. The query API routes automatically based on the time range you specify. Searching the last hour is the Elasticsearch. Compliance audit from 8 months ago, S3. The caller doesn't need to know which tier they're hitting. After this is concept 3, that is Elasticsearch indexing strategy. Don't put all your logs in one giant Elasticsearch index. Use one index per day, like logs 2024-0115, then logs 2024-0116. This seems like a small implementation detail, but it has massive operational benefits. You can delete old log data by dropping an index instantly, zero overhead. You can force merge old indices to compact them and save storage. You can move old indices to warm nodes automatically, and query routing becomes free. Searching the last 7 days means Elasticsearch only scans 7 indices instead of the entire database. This is called index lifecycle management, and Elasticsearch has built it in it. Configure it on day 1, retrofitting it later on a running cluster is very painful. Now the logging system needs its own monitoring. And who watches the watchman? Here are a couple of the log dashboard. The panel 1 is the log agent. It shows the Kafka lag per service. If any service has lag greater than 10,000 messages, the agent is struggling. Panel 2 is Kafka consumer lag. If lag grows, ES indexing is falling behind. Then panel 3 is ES indexing rate versus the ingestion rate. This should match. Divergence, then it's a backlog. In panel 4, S3 archive success rate. Any failure is equal to logs that won't be in cold storage. The most important alert is if Kafka consumer lag is greater than 100,000, it means that logs are 90 plus seconds delayed in search. A logging system that's 5 minutes behind during an incident is nearly useless. You are trying to diagnose a live fire with stale intelligence. Monitor the pipeline lag as a first class concern. Kafka consumer lags above 100,000 messages means your search results are running 90 plus seconds behind the reality, and that needs to wake someone up. Here are some of the failure points of this design. The first failure could be a log agent disk is full. The log agent buffers locally before sending. What if a service starts emitting errors rapidly? Agent buffer fills, agent then starts dropping logs. Or worse, the service own log files fill the disk and the service crashes. The monitoring kills the thing it was supposed to monitor. This fix is non-negotiable. Set disk space limit on log files with rolling station and a max size. Agent buffers in memory with a small disk fallback. If the buffer fills, drop older logs and alert, but never let logging take down the service it's watching. The second failure is Elasticsearch indexing lag. What if a deployment goes wrong, triggers an error storm, and suddenly you are at 10x normal log volume? Elasticsearch can't keep up. Consumer lags grows, the log appears in search with a 10-minute delay right when you need them most. Kafka is your safety net here. The logs aren't lost, they're queued. Autoscale ES ingestion nodes based on the Kafka consumer lag. Accept temporary delay rather than the data loss. Secondary fix might be always use the Elasticsearch bulk API. Never index one index at a time. Batch 5,000 documents per request minimum. The third failure could be the cardinality explosion in search queries. An engineer adds a user ID as a structured log field. Reasonable idea, right? Elasticsearch creates a separate inverted index entry for each unique user ID. With 50 million users, that's a 50 million index entries. Memory exhaustion, cluster destabilizes. This happens more often than you think. The fix is enforcing field cardinality limits. Block the indexing of fields more than 1000 unique values by default. If you genuinely need user level querying, store it in a separate high cardinality store, not Elasticsearch. Here are some of the improvements which we could do in the design. This is very important if you are interviewing for the senior level, and this is a must. You should know your own fallbacks. The first one is structured logging enforced at the framework level. Don't leave it up to each developer to add the right fields. Build a company wide logging library that enforces the structure. Required fields are service, trace ID, level, and timestamp. Optional fields like duration, milliseconds, then the error code are available but optional. Deploy it as a standard and all services inherit consistent log automatically. One config change propagates everywhere. The second improvement we can discuss or we can make it is adaptive log sampling. During normal operation, log everything at info level and above. During an incident or a high traffic event, log a 10% sample of the info but keep 100% of error and warn. You keep the signal you need, errors and warnings, while reducing the storage cost by 5 to 10x on the noise. The trick is making the sampling rate configurable at runtime without a redeploy. One more improvement we can do is trace the correlation across services. Pass a trace ID to every service call and include it in every log line. Now, a single query for trace ID ABCD123 shows every log line for every service for everyone's users request in chronological order. If you see here, it shows all the logs in chronological order. That turns distributed log into a coherent story. From something failed somewhere to payment service DB timed out on this specific request at this specific millisecond. All right, so logs are the most verbose signal in your observability stack. Not as efficient as metrics, not as structured as distributed traces, but they are the only thing that gives you the full story. At 10:30:46 on host prod east 1A, the payment service failed to connect to the database after 30 seconds during a transaction for order 12345 initiated by trace ABCD123. No metric will tell you this, no trace tell you this. Remember where we started. 90 minutes of grepping across 200 servers for one misconfigured variable. A well-designed logging system turns this into a 5-second query. Build it so the story is easy to find because at 3 a.m., staring at red dashboards, the story is all that matters. So, see you the next time.